So hello everyone. Firstly, I would like to thank the organizers for this opportunity, and I'm a research scholar at IIT Madras, and today I'm giving my presentation on the title Bound Layers in Thin Polymer Films. So this presentation will be a little different from the rest of the talk because it's highly experimental. So let me go very slowly. I'm sure like many of us are familiar with polymers. Basically, polymers are nothing but macromolecules which are composed of repeating subunits called monomers, which form a long chain, and this is a real linear polymer chain that's recorded in a liquid medium through atomic force microscopy. So now let me go into the particular aspect of this polymers. This is confinement. Now polymers generally, when they are in bulk state, they can undergo multiple conformations because there is no degree of, there is all the 3 degrees of freedom. However, when we confine these polymer chains like along the thickness direction, we try to bring the polymers in its length scale like Rg of the polymer. They are commonly known as one-dimensional confined polymer films, and similarly we can have a 2-dimensional confinement confining from 2 directions and 3-dimensional confinement like in nanopores. In this talk, I would like to focus in one-dimensional confinement. So one-dimensional confinement can basically be of 2 types. They are either a freestanding polymer film in a nanometer thickness 2 microns, or substrate supported polymer thin films. So this is a very simple schematic I've drawn where you have a polymer chains deposited on top of a substrate, hard substrate in general, and these chains and films, they are called polymer thin films. They are generally annealed at temperature above their glass transition temperature to promote the absorption of the polymers to the substrate. So why is this important is because of this substrate, hard substrate, the polymer chain dynamics, they are highly affected by it. So the polymers, they undergo very slow dynamics. So one of the effects that comes very important is the interfacial effects. That's as you can already see, there are 2 interfaces, one with the polymer air interface and another with the substrate interface. However, the substrate interface are much more dominant over the upper interface. Now why is this important is because we know that polymer thin films are widely used from technology to even day-to-day applications. So understanding the structural and dynamical properties, like I need not mention how important understanding glass transition temperature, de-wetting and crystallization and swelling are so important in polymer thin films. So that's why understanding this interfacial effects are very important. Another hand is the technological application, because these polymer films, they are widely used in like controlling the addition or depositing of very thin films. So based on this importance, there is a consequence of such an interfacial effects is, if you look at the cross section, there is a certain layer that has been recently found is such a known as an adsorbed layer or a bound layer, which is next to the polymers, next to the substrate, and which is in few nanometers thickness. Now the condition for this formation of such an adsorbed bound layer is because if the contact, suppose this is a polymer chains, if the contact energy between the monomers, say suppose these green monomers are adsorbed to the substrate at that instant of time, the contact energy is greater than the thermal energy of the system, then this polymer chains or the monomer get adsorbed to the substrate. However, for each monomer, they can reversibly adsorb and dissolve, but the whole polymer chain to dissolve from the substrate, the energy cost is very high. So that's why this results in a certain layer which is known as typically bound layer on top of the substrate, and the chains are so adsorbed to the substrate that the chains reaching equilibrium takes a very long time, and the process is, equilibrium process is inaccessible. So now why do we need, we need to investigate this bound layer. So in this talk I would like to focus on the investigation or probing of this bound layer. So now as you already see that this film overall itself is in nanometer films, and determining this bound layer is quite challenging. However, there is a very common approach which is known as Giselin's approach. I'll come back to this again. So basically what you have, suppose initial studies were done on polystyrene in the presence of a very good solvent which is toluene. So we basically take the polymer film and then you rinse it or immerse in good solvent to determine the layer. So this is an atomic force microscopy topography image where you can see the adsorbed layer completely different from the rest part of the film. So this is like once you form the adsorbed layer, you scratch it off the liberating part to determine the step height. So this is more like a destructive kind of a measurement. However, it gives one way the estimation of such an adsorbed layer. I'll come back to this approach later on. However, now what we propose here is a non-destructive and indirect method to probe this bound layer and how close we can approximate. Now, for this we propose alternate method through the swelling kinetics of this polymer films, and from which we can determine the thickness as well as density of this bound layer. Now, some of us might be new for swelling of polymer films. So, swelling is basically a copper transport of mass transport as well as segmental motion of polymer films. What I mean by that is that suppose you have a polymer thin film and it's a hydrophilic polymer film, and you bring in presence of water molecules. Now, because of this polymer likes water, and then it's a osmotic pressure, and then the water molecules diffuses in, and it's a one-dimensional diffusion because the polymer thin films are so thin that the interfacial diffusions are very low, and diffusion are mostly from the top planar surface. And because of this, the polymer chain expands and there is a high diffusion from the top surface, and this increment in the thickness can be determined by certain techniques. Now, initially we think that if there is a certain bound layer next to the substrate which has to be compact, dense and immobilized, it should not undergo such kinetic process of such a swelling. So now with this, I would briefly go to the methodology because it might be, so just the methodology because many of us are, some theoretical. So spin coating process is basically, okay, the polymer I take here is a hydrophilic polymer which have a hydroxyl group, as you can see, so it likes water. So the spin coating process is a very simple process for fabrication of polymer thin films, which is a very rapid process through centrifugal force. You put a polymer solution and then through centrifugal force you can get a film in nanometers thicknesses. So with this we prepare a thin film, and in this talk, due to for the interest of time, I will just discuss one of the system where we anneal the polymer film at 120 degrees centigrade for 12 hours. And the characterization technique which we commonly use for polymer thin films or such nano films are spectroscopic ellipsometry, which is basically you have a for the moment we can forget the chamber. Just imagine a linearly polarized light, a non-polarized light incident on a sample, and the change in polarization state is what recorded by this instrument, and we can get ellipsometric parameters psi and delta, and then fitting it by optimized model. So a model for us well fits is the Cauchy isotropic model, which says it's a highly transparent polymer film, and we can simply fit this with data to extract the thickness, refractive index and roughness. Now as a complementary technique we have X-ray reflectivity where we the way the probing incident rays are the X-rays instead of white light here. So then we can determine the polymer thickness, density and so forth. So coming to now the experimental part of it, I'll go a little slower maybe initially, like we have a chamber since we are trying to study the swelling of this film, so we need a closed chamber. So we take the polymer film, keep it here, and then we start the measurement like ellipsometry and reflectivity. Then we take two water cans where we try to fill it water cans and then close it and then let the water saturate. Once it saturates, the polymer thin film expands, which I was initially showing there. Polymer thin films expands when generally in the along the thickness direction because of one-dimensional diffusion. Now how do we confirm this? We confirm this by this technique ellipsometry, where you can see psi is one of the ellipsometric parameter which is highly associated with the dielectric property or the refractive index of the polymer film. Now this green symbol is for the dry sample where the polymer film is dry. Now this is the spectra which we obtain. And as we increase the, as we record as a function of time, the water molecule diffuses in, undergoing increment in the polymer thin thickness, and since the polymer refractive index is basically higher than the water. So when water diffuses in, the overall refractive index goes down of the system, which can be identified by the shift in the this psi delta peak towards the psi peak towards longer wavelength. As in complementary, we have also delta and delta parameter, which is basically the phase shift of the S and the P polarized component of the electric field, which shift towards longer wavelength indicates that the film is becoming thicker and thicker, and we can fit this to data parameters to obtain the polymer film thickness evolution. So this is a conclusive plot for this section, where you see that initially we find that this is the instantaneous film thickness as a function of time. Time is the exposure of the swelling, and we perform for like around 650 minutes, and for different range of thicknesses here. As you can see here, we have gone from like 31 nanometers to like 263 nanometers. These are dry film thicknesses. Now interestingly, what we see is that when you have a very thin film, it seems to swell very less. However, with increment in thickness, the swelling keeps on increasing. Now this doesn't follow the understanding from macroscopic thermodynamics, which says that if the polymer and the substrates, they are same and the interactions are same with the same preparation method, swelling should be same for all these polymer films, and we are much above the RG of the polymer thin films. So swelling should depend only on the thermodynamic parameters like temperature, pressure, and so forth. Now we come up with an idea that could we describe or could we propose a function, a so-called single effective function that would incorporate the swelling of all these polymer films, provided there is a layer, we name that to be bound layer, which doesn't contribute to the overall swelling of the film. So then what we do, we give this simple equation where try to subtract out this d of s bound layer thickness, and then what we do is that we basically, we plot an instantaneous film thickness as a function of dry initial film thickness. Interestingly, we see that for the range of different time intervals, we see that it lies in a straight line, and we can bring this equation in terms of a straight line and then fit it by using this equation to determine from the slope the C of t, the effective swelling function, and then from the slope and the intercept the d of s, the bound layer thickness. With this we further perform for longer range as well, and then we obtain this final part where we see that C of t is the effective swelling function. That means that no matter what the thickness of the polymer film you take, all the films, they swell with the same extent with this common function, provided there is a layer, that d of s, which turns out to be around 6.8 or 1.7, that doesn't contribute to the swelling. Now we can verify this later on by a direct approach, which I'll come in few slides. Now before this, to confirm this with some independent technique, we have used X-ray reflectivity. So reflectivity, where you have a reflectivity as a function of a scattering wave vector transfer, which is a Fourier transform of this angle of grazing incidence. So these oscillation fringes are basically the so-called kissing fringes. It's because of this you have a film and you have an interference of X-rays from the top and the bottom interface, and these are for different thin films. As you can see, they are just shifted for clarity, and we from the width of the oscillation fringes itself, we can determine the thickness as well. However, we can further fit it by using the so-called Parrott's formalism, which is pretty common, and we fit it very well by considering a two-layer model, which is all over. It's a four-layer model because you have a silicon substrate SiO2, which is 2 nanometer, determined from Se, and then and the two layers. Now this can be very well fitted by considering this bound layer and a polymer layer. By fitting this, we can determine the so-called electron density, which is nothing but basically how close the electrons are packed together. So as you can see, this is electron density as a function of this z is the distance from the substrate. So basically going from substrate towards the polymer film, you can see a very high electron density, which is the SiO2 layer, and then sharp fall towards the upper polymer layer, which identified as the bound layer for us, and then the upper polymer film for different range of thicknesses. So the electron density of this polymer film, the bound layer comes up to be around 0.4969 electron per angstrom cube. And another thing what we can see here is that the bound layer thickness are pretty comparable for no matter what the thicknesses you take, initial thicknesses, and and then you have an upper polymer layer, which you see that basically if you have a thinner film like 31 nanometer, the electron density is relatively lower, and as keep on increasing thickness, the electron density keep on increasing. This we believe that by looking at some literatures, initially they have also reported that if you have a thinner film, the electron density is very high. However, if you have a thicker film, the electron density keeps on reducing. That means it's simply known as a confinement effect. If you have a thinner and thinner film, the polymer chain densifies, so that contributes to the higher electron density. Now the bound layer thickness which we compare is pretty close from an indirect approach. We try to confirm this by which I initially mentioned briefly by this Gizelin's approach, direct approach. So the basically just what you mean is basically you take a polymer film and then you rinse it with, in our case it's a hydrophilic polymer, so GI water, and then submerge in this solvent, in this water solvent for a different time intervals, so that we let the adsorb chains to remove as much as is possible. So when we look at and we do the reflectivity and SE measurement on this chains, this film is also known as a residual film. So if we look at the residual film thickness as a function of the time of this treatment, which is solvent leaching called, we can see that as I was initially saying, that no matter what thickness you take, initial thickness from 31 to, you can see 1 order difference from 31 nanometers to 358 nanometers, we believe that there is a certain layer that's dependent only on the polymer and a substrate interaction, independent of the thickness. So here we can clearly see that range of thicknesses after certain interval of such an etching, the loosely adsorbed chains, whatever is remained on the top, can be washed off by such a treatment, and then the remained chain, it remains pretty long for like 48 hours. Such reports has also been found in other studies. So these layers are so called bound or the adsorbed layers near to the substrate, and the thickness are pretty comparable from the two techniques. Then what we do is that we took that layer film, this film, and then did an X-ray reflectivity to find the electron density. So we see that, as you can see, these are 358, these are initial film thicknesses, and done X-ray and these are the residual film spectra. We see for all different thicknesses, this thicknesses comes out to be pretty close, and the average out to be somewhere close to what we have already found. So then if you look at the electron density, which are again close to our fits where we consider the whole polymer film, I mean the bound layer buried inside the polymer film. Now finally few slides where I would like to compare this same study in an unannealed and annealed system, because it's very affected by annealing. So just to briefly show the collective normalized swelling, you can see that the unannealed film swells maximum, and after 10 minutes of annealing, just 10 minutes of annealing, you can see the swelling is reduced. And then for further annealing after 1 hour, there is no significant change in this swelling spectra. Similarly, when we look at the electron density, we see that the unannealed film, which is about 59 nanometers, there is an electron bound density which is relatively much more smaller than the annealed film. What does it say is that for now the take home message is that annealing seems kind of packs the polymer chain towards the substrate, which leads to increase in the electron density. Now to conclude, for today's talk, I just focused on this part of this study where we found the thickness of the bound layer to be, for an annealed film of about 12 hours, we found that the thickness is pretty closer. And then I'll come to our explanation, like why there's some difference. Now let's focus in the unannealed part. Now you can see here that swelling kinetics shows that the annealed bound layer should be about like 15 plus minus 3 nanometers. However, the Giselin's approach, which is a direct rinsing of approach, which says it just should to be about 2 to 3 nanometers. Now some literatures have found that these are so called flattened layers or something like a dead layer, which is very tightly near to the substrate. So what we think is that from the swelling approach, we are actually not just probing this layer, along with this we are probing certain loosely adsorbed chains that can easily be washed off by such a harsh or direct Giselin's approach using a strong solvent. So now when we try to fill in the gaps with different annealing temperature, what we see is that if we let's focus on the swelling kinetics first, we see there is a drop in this film thickness and then saturates after just 1 hour of annealing. That means this bound layer which I talked about, the loosely adsorbed chains, now they kind of densify, and we saw that the increment in the density as well earlier slides. So this leads to the decrease in the thickness of the polymer film. So the overall bound layer thickness kind of saturates after a certain extent. Now if we look into the from the Giselin's approach, what we see is that is the red circles. So we see that initially it's very low, as I was saying, because now in this unannealed films, the loosely chains can be easily washed off by this water, and then there are but certain sites which are remain on the chains. That's why the electron density is very low. Now what we do is that we try to anneal the film, and we see that the sudden increase in the bound layer thickness and kind of saturates after a certain period of annealing time. So now why is there an increase in this layer thickness with annealing is that some other reports have also found this, but the overall understanding is that when you anneal it at a longer period of time, more and more polymer chains they can get adsorbed to the substrate, and since there are limited sites because there are already an inner layer which has occupied the sites, so the later incoming chains which we are generally dealing with higher molecular weights, so chains are pretty long enough, only the segments of the chain they get adsorbed to these remaining sites or available sites. However, the part of the chains they are dangling out, these are known as the tail part of the chains. Now this overall contributes to this the adsorbed layer, because even after Giselin's approach, these chains cannot be removed because it has been the temperature is sufficient enough to let this adsorption. With this, I would like to conclude my talk, and then the summary is that by swelling we can simply kind of estimate this bound layer thickness and density, and then when you have an unannealed film, there seems to be a significant difference between the two approach, probably because swelling is not just of this, not just determine the thickness of the inner flattened layer, however also from the loosely bound layer. Then when we anneal it, when we anneal it, this thickness increases, as you can see, increases with thermal annealing, which because more and more chains gets absorbed to the substrate, and it leads to the contribution to increased thickness. That's I would thank you. I mean, I would like to acknowledge my actually supervisor, Professor Dilip, and also Professor Sitish from Japan. We have collaboration. Then IT Madras, of course, and CSI UGC for my funding. And thank you, everyone. I'm happy to take questions and suggestions.
Thanks, Sonam, for a very interesting talk. Time for some questions.
Sonam, nice talk.
Yes,
in slide 7,
yes,
so you had mentioned that you're using some fitting to get
Yes.
your data,
Right.
and there I think you're showing data for different times. I think the swelling.
Yes,
yeah,
sir.
no, I think the next slide.
This one. Yes, sir.
No, the next slide. Next slide.
7.
The data that you had, right?
Oh, yes.
That was for different. See,
Yes,
this after 5 minutes and 180 minutes, right?
Right.
So I think one of the parameter that you mentioned goes into the obtaining this fit is the refractive index.
Yes. Yeah.
The refractive index that you take for fifth minute and 180 minute, is it the same?
No, they are different, sir. Actually, it exponentially decays down.
Okay.
Generally, because the polymers have a higher refractive index than water generally.
Correct.
So of course, I mean, and then when swelling starts, the water diffuses in. So the overall the samples refractive index goes down because the water diffuses in. So we see an exponential fall because if you look at the swelling also, we have initially a very sharp diffusion, which is generally known as a Fickian diffusion. It diffuses very fast because of the concentration gradient. And the later part is basically the polymer relaxation. The chains kind of relaxes and try to accommodate more and more water. So we see similar spectra even for refractive index, that it falls sharply initially, then it slowly decays down. Sorry, I don't have the plot here.
No, sure. Yeah. Thanks. Yeah.
Thanks.
Hello. Yeah, nice talk actually.
Yes.
Can you this swelling rate, right? Can you control with the if you control the humidity of the chamber?
Yeah, we can control. Actually, we.
So
what
how
we do-
the swelling rate will we have actually? Most of the case your swelling rate is linear, right? It was
Yeah.
increasing. So if with humidity, how it will change?
Yeah, actually what we are doing is we are studying in a saturated humidity. It's a very
Okay, yes.
closed chamber and very small, and we have a humidity sensor to sense saturated. Within few minutes it's saturated. But that can be studied. What we have done there is that you vary the humidity and through a very static measurements. Like you take a very low 10% humidity, maintain it, and then see it, how does it dissolve, and then go to up to even 99% humidity. So that's static humidity measurement.
So yeah, let's say you will maintain a 10 or 20% humidity. So after some time, there will be no humid or something. So is the swelling will be stopped? After
No,
that or
yeah,
something?
that's an interesting thing because generally in Chennai when we do the humidity itself is 40-50%.
Yes.
So the thickness is somewhere around, say suppose this is 189 nanometers, and when we do measurement at a very low humidity, we have a chamber, we pass through dry nitrogen. We can control the nitrogen flow to control the humidity.
Yes.
So when we go like 30%, 20%, 10%, we can see there's a decrease in thickness because now there's absorbed water that comes out actually.
Yeah, that I was
That's
thinking.
yeah.
Yes.
Yeah,
Thank
we
you.
can
Nice
study
talk.
that. Yes.
Yeah, it's regarding to what you explained at the end. It was not very clear to me why, after annealing, there was this difference in the thickness with the glycerin and the
Yes.
swelling. Because I would have thought that, as you said, with glycerin, and glycerin can affect at short times, but at the end, it's mostly controlled by how chains are adsorbed and interfere with the pre-adsorbed layers. I would have thought the results should have been quite generic.
Quite generic, yeah. So what do we think at the moment is that this is the one, I guess. What do you think is that now the difference is that swelling is a very indirect measurement, and we believe that the layer we are determining is that the bound layer shouldn't contribute to the swelling. However, from Giselin's approach, we find that there are certain tail part of the chains. These are the tail part of the chains because it's a higher molecular weight. The chain is longer. Part of the chains are adsorbed. They are this is known as strain, and these are called loops. And these are part of the chains that are adsorbed, but part of the chains which are called tails, they are dangling out. We believe that these chains, they can undergo some mobility that contributes to the swelling. That could contribute to the swelling. So that's why the remaining, maybe from the swelling what we are determining might be just the tightly adsorbed, which doesn't contribute to the swelling completely. However, from the Giselin's approach, which is completely removing of the above layer, the part of the dangling chains will still be there because its segments are still attached to the substrate, which is because of the annealing. So that's why I think we see the increment thickness, because now we are determining the whole layer thickness. At the moment, it's just speculation.
So on that same line, did you try to explore different molecular weights of PBA, or do you plan to explore in future?
Yes. Actually, what studies have found is that we have not done for different molecular weights, but what studies have found that if you have a higher molecular weight, the degree of degree of polymerization n is more, right? So it has been found that the adsorbed layer thickness goes as square root over n. So more the n, the longer number of chains, this adsorbed layer thickness are relatively higher. And also the kinetics also matters, like it takes longer time to reach saturation. You need to anneal longer period of time. So those studies are there.
Yeah, that will be something
That's a nice
interesting to
question,
explore in future.
Yes.